an explanation of modeling, because you know you're year 12s now, you've done a bit of modeling. So I just want to explain what you've done and the power of it, right? And the first thing is, let's imagine I don't know, I'm an engineer at a component company, right? So components are the little itty bitty things, little itty bitty bits of electronics inside big pieces of electronics, right? So I make like millions of components, and I just want to study it, right? You can only make something cheaper and more efficient if you study it, right? So let's say I've got this component. Okay, now I want to study what happens to that component after it's changed to the fourth setting. So, like gear 1, 2, 3, 4. You know how you turn a dial. So when it's turned to the fourth setting, what happens to it? And I find, you know, I don't check one component. I do a bunch of components a lot of times, and I find that before being turned to the fourth component, it's around 6 watts. The minute it's turned to the fourth one, in half a second it goes up to 9. In 1 second it goes up to 11. In 3 seconds it goes up to 14. But then after 3 seconds it starts to come down, right? Maybe there was an initial surge and it comes down. And it goes down in 3.5 seconds. It's at 11 watts, and at 4 seconds it's back down to 6 watts. So this is the initial phase. What happens as soon as the component. I don't know anything about components, by the way. I'm not a physics guy, so I'm just completely making this up, right? So sorry if components don't behave this way. You'll see the point I'm trying to make. So let's say my component behaves this way. It does this as soon as it's moving. Setting, right? Now this is data I've collected, which is really good, and I've plotted it. You know, maybe what I can do is I can join the dots, right? So that's the next thing you would do, really, right? You would join the dots, right? And then you get this graph of your data and what it's done, right? So you can see that it's done. But can you tell me something? In 0.1 seconds, how many watts are taken up? So if I go 0.1 and I go up, I can't really read that. Is that 6.1? Is that 6.2? Is that 6.3? It's not really like this. This is very basic, and it's limited what you can do with this. What an engineer wants to do is he wants to start with this, but then he wants to model it. He wants to say, well, that looks like a parabola. Maybe I can model it with a parabola, right? Maybe it can have its turning point over here. It can be an upside. Ooh, let me do all that maths that we've already done this year in graphs. Let me do all that maths and come up with this, right? So instead of using this, he's using this, and that might seem like a whole lot of work. Like, I'm sure in the 6th grade, like in year 6, you would be able to plot 1, 2, 3, 4, 5, 6 points and join them with a ruler. Why do we put all this energy, to the point that only a year 12 student can barely do this because it's quite advanced, quite difficult? Why do we put all that energy into having the parabola instead of the plotted points? And that's what I'm going to show you today. How much more powerful it is for the engineer to say, this is what I got, but I'm going to estimate it with this from now on. From now on, let's begin. So we can see that that we've decided to use an equation. We've decided to use negative 2x squared plus 8x plus 6. And the power of using the power of using this, our equation, rather than these points, is truly it's manifest, and even at year 12 level. Okay, let me tell you a few things about a function. Now, that looks like a lot of work. Like I said, instead of just joining dots, you're coming up with an equation. Not this equation, but anyway, like any function. That's a lot of work, right? Now, firstly, what's a function made up of? It's made up of f of x or y. Now, they're the same thing. So I want you to think of them as the same thing. Like, I know there is for year 12 purposes, they're really very much the same thing, right? Now, a function has y in it and x in it, right? Remember y and f of x, I want you to really put the same. But the cool thing about a function is that if you have x, you can find the corresponding y value, and if you have y, you can find the corresponding x value. And I just want to show you those two very common uses in action. So we have our, this is our graph, this is the equation we found. These are all the tricks we can do with our function. We're focused on the function now. We'll get to the gradient function and what it can do in a minute. So the function, if you have x, you can find y, and if you have y, you can find x, right? So if I have the time, I can find the watts consumed, and if I have the watts consumed, I can find out how long that's the case. Now this was our, we put a lot of effort to come up with this equation, and now the easy part is, let's say, I know x is 4, right? The time is 4 seconds, and I want to know the y. I want to know how many watts are consumed after 4 seconds. And that's really easy. In order to do that, you take your equation, and wherever you see an x, I want you to write a 4 instead, right? Because we know x is 4, so we're going to make that a 4. Just make sure when you do it that you put it in brackets, right? So I'm just going to, everywhere I see an x, don't just do it the first time. Every single place you see an x, I'll put a 4. And then look at your answer. Now, one of the very big skills in calculus, especially for B-Med students, is looking at that and figuring out, do I need to do any more algebra, or do I just put that in my calculator? Now, the fact that it says y equals and there's only numbers after that means you just have to put it in your calculator, right? So what we're going to do is we're going to put exactly that. We don't have to put anything extra, anything less. Put exactly that in our calculator, and we'll get, just say that again. You need to be able to recognize that this does not require any algebra, and it'll get you, put that in right now. You can practice if you want. Putting that in, it should get you y equals 6. What does that tell you? That tells you that when x equals 4, y equals 6. When the time is 4 seconds, the number of watts consumed is 6. And you can see that on our graph. You can see that when x is 4, y equals 6, which is amazing. And the thing is, sometimes, I purposely chose numbers that give whole number answers in this PowerPoint. Sometimes we don't have whole number answers. Okay, let's look at this. Let's say I want to know after 0.1 seconds, right? After 0.1 seconds, I want to find out how many watts are consumed. Well, I'll just go through my usual process. I take my model equation that took a lot of effort, and now that I've done that effort, it's really easy. Everywhere I see an x, I just put a 0.1. Don't forget the brackets. I'll put it here as well. Sorry, I'm writing this on a laptop, so but it'll get the point across, right? So that's it looks a little nicer over there. Just a negative 2x squared, but x I changed to 0.1, plus 8x I've changed to 0.1, plus 6 that has no x, so I don't put 0.1 in there, and you get y equals 6.78. That is a far more exact answer than if you tried to read it off the graph. I'm going to show you real quick. Let's magnify this area here. Tell me reading, so someone might have said in the last one, well, that's okay, I could have just read it off the graph before. But 0.1, 6.7. Now, an engineer has to be exact. They can't say, oh, well, that looks like 6.9. We can't do that in this day and age when we're trying to perfect our processes. When you go to a factory and everything has to be perfected, the efficiency has to be, we can't guess 6.9. We need to know exactly, and that is one of the that is one of the huge advantages of modeling. I mean, this is so cool. X equals 0.1 and the watts consumed is 6.78. I have a very detailed, what you can say, very accurate answer. Like, the degree of accuracy is much more than if I just read it off the graph. So isn't that amazing that any x I want, I can find the corresponding y as long as I have this equation? That is why we've been through all that effort in graphs at the beginning of the year, trying to look at something and make an equation for it rather than like a drawing for it, right? Drawings are interesting, but equations are so much more, right? So what did I say? If you have x, you can find y, and I also said if you have y, you can find x, right? So we have our equation. Let's say I want to know 12.
Okay, so I'm saying I want to know at what time are 12 watts consumed. So what do? I take y equals 12. So I take y equals 12 and I just put it on top of wherever I see a y. In this case, there's only one y. I put it over there. Now, what did I say? Especially for B-benders, the big part for you is to sit here right now and say to yourself, do I need to do algebra? And the answer is yes. It's a quadratic equation. So first thing is you need to recognize that you need to do algebra. The second thing is you need to recognize it's not a linear equation. This is huge. This is absolutely huge for you getting these credits. A linear equation is when you get the x all by itself. So if you remember, we had something like 4x minus 2 equals, let's say 10. Okay, and what did we do? We took the 2 to the other side, right? We added 2, right? Or some people say add 2 to both sides, whatever. We took the 2 to the other side, so it became 4x equals 12, and then we divided by 4x equals 3. That's all fun and fine, but if you do that, this is why a lot of you will have struggled with algebra last year. Linear equations have one methodology, quadratic a completely different methodology, and if you're mixing them up, then kiss your credits goodbye. You can kiss your credits goodbye. You need to know that this is what you do if you see it. Now, how do you know it's linear? There's no squares, there's no cubed. Remember, it has to be an expanded form. So if there's brackets there, first it's expanded. Because if you expand it and it becomes a quadratic, you should deal with it in the non-linear fashion. But if there's no x squareds, no x cubes, it's a linear equation. Linear equation, you got to get x all by itself. If you do that here, and you try to get, you move the 6 to the other side, if you try to get x all by itself over here, you're going nowhere. You are going absolutely nowhere. In any nonlinear equation in calculus, what I want you to do is I want you to make it equal to 0. Really different, right? Because if you were using this method, you would take the 6 over here. Well, what did I say? Leave the 6 over there. I want this to become a 0. Sometimes you need to move x as well as a number. Sometimes you have to move x. Whatever is here, I want it to say 0. That's the first step. So what we do is we make it equal to 0. To do that, I need to take the 12 to the other side. Okay, 12 becomes a minus 12. And remember, the 12 doesn't exist over here anymore, right? It doesn't exist. It used to, but now it doesn't exist. So there's 0 on this side. These are like terms. Don't apply the 12 to this or this. You apply it to that. So I get negative 2x squared plus 8x minus 6. Okay. Now, good news for you. All you have to do is put it in your calculator. I think everyone in the class can do that. But what was the tricky part? What was the part that would muck it up for you? You would have taken the 6 to the other side, and you would have taken the 8x to the other side, and you would have thought to yourself, how do I get the x all by itself? No! We do not get the x all by itself. Sometimes we do. In linear equations, we're trying to get the x all by itself. But in any non-linear equation, we make it equal to 0, and in calculator, we trust. Okay? So I'm going to put this in my calculator right now. Bang, 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 bang. And it comes up with 2 answers, 1 and 3. And that makes sense because if I look at y equals 12, it still says y equals 6. Silly Mr. Cheat, I forgot to, this is the problem with copying and pasting. That's for the last one. So when y equals 12, x can equal 1 or it can equal 3. It happens 2 times. The watts consumed first, there's the first time there's 12 watts consumed is after 1 second, and then because it starts powering down or whatever, after 3 seconds again it's 12 watts. Again, absolutely amazing. If you know x, you can find y, and in this case, we knew y. We were able to find all the x's for which that is true. Remember what I said about this algebra part. If you do not focus on this, you can kiss the credits goodbye. Okay. That's all the function. What about the gradient function? You know, that we've been differentiating all these days and you didn't know what you're doing or why you're doing it. This is why. And it answers why we model. Because if you don't have a function, you can't create a gradient function, right? So if you didn't model with a function, you couldn't do any of this either, right? So this is also some of the benefits of modeling, right? Of creating an equation rather than a picture, right? So the cool thing about the gradient function is if you have x, you can find the gradient. The gradient can be it can be the word gradient. M means the same thing, gradient. F dash x, when it equals a number, that's the gradient. Or if you have the gradient, you can find the x value for which the gradient is such, right? So let's look at the first easy one. What we can see is that let's say I have a question. I have the y-axis, and I'm looking for finding the gradient when x equals 1, right? So firstly, you have to figure out what you need. You need your gradient. If I go back to my thing, okay, what do I need? I need the gradient. Oh, I can find the gradient. What do I need? I need x. What do I need to do with x? Put it in the gradient function. I get the gradient. How exciting, okay? So I asked myself, which parts of that do I not have? Well, I don't have a gradient function, so why don't I create one? Okay? And I differentiate, and we're really good at that in class, so you guys are doing great, right? And then the next thing, what did it say? It said, substitute x equals 1 into the gradient function. Now, here's another tricky one, especially for me, man. You guys got to be really careful. If you put x equals 1 into the function, you're finding y, and that's not what the question asked. You have to put x equals 1 into the gradient function. Right? Let me just get a laser. You need to put this here, not here. In your carelessness, if you put it in there, you get the whole thing wrong. Could cost you credits, right? So what I'm going to do is I'm going to take x equals 1 and just substitute it in. So wherever I see an x, I'm going to put a 1, right? In this case, it's only one time. Put it with brackets, right? I'm so bad. Right. Put it with brackets. This is what it'll look like. Negative 4x, but wherever I see an x, put a 1. Really big trick. If there's more than one x, you need to put more than one 1, right? Or whatever you're substituting, right? Sometimes kids only put it in the first one, okay? So, but in this case, there's only one x, so negative 4x plus 8. Now you ask yourself, do I need algebra, or do I just put that in my calculator? Looking at it, okay, it looks like I just need to put it in my calculator. I can sign entirely with numbers and other types of 4. So I put it in, and I get y dash equals 4. So this tells me that when x equals 1, which is over here, if I go from x equals 1 and I go up from x equals 1 or down till I hit my function, over here the gradient is 4. Now let's put a tangent at that point, and I'm just gonna zoom it in. The tangent has the same gradient at that point, and what I'm gonna show you is that the tangent is 4 over 1. 4 over 1. 4. So the gradient is 4. That is absolutely correct, and it's an amazing thing that as long as you have x, you can find the gradient. And remember what I said, you could have done that for x equals 2, it would have found the gradient over here. You could have done it for x equals 4, it would have found the gradient over here. And that's one of the really cool things about an equation. Last really cool thing that a gradient function can do, if you have the gradient, you can find when that's true. When is the gradient that much, right? So let's look at this question here. It says the gradient is negative 4, and it's saying, what's the x value when that happens, right? So remember, this is a constantly changing gradient. Somewhere on there, the gradient is negative 4. So we know it's going to be in this half. Somewhere on there, the gradient is going to be negative 4. But where? Okay, so what did I say? If you put gradient equals negative 4, let's look down here. What we're saying is we want the x value when the gradient is negative 4. Well, we can find that if we put the gradient into the gradient function. Well, I have the gradient, so now I just need a gradient function, right? To do that, I'm just going to differentiate. By the way, if in your entire question you're not differentiating or anti-differentiating somewhere, be very suspicious. it's a calculus. If there's no calculus, the question probably shouldn't be in, right? So be very suspicious. It could be their mistake, but just be very suspicious, right? Okay, so we get y dash. So this is the gradient function. What did I say? Put the gradient into the gradient function, and it'll spit out the x for which that is. Okay, cool as. So I'll take gradient equals -4. That's this thing over here. So I'm going to put -4 instead of that, right? And now you ask yourself, is that calculator work or algebra work? It's algebra, right? Because there's like, it looks like it needs solving, right? So is this linear or is it quadratic, cubic, non-linear, and all that stuff? It's linear. So this time I don't get this side equal to 0. I get the x all by itself. Little bit of algebra, make the 8 disappear. It becomes like that. Make -4 disappear. It becomes like that. So I know that x equals 3. What that tells me is that when is the gradient -4? It's at x equals 3. It's at this point over here. I'm probably going to have you up. At x equals 3 over here, the gradient is exactly -4. Let's put a tangent to see. That's a tangent. And it looks like it's going -4 over 1, -4 over 1, -4 over 1. The gradient is -4. Oh, fantastic. And so this is our toolkit. If you know how to use this toolkit, you will get it achieved, maybe even a merit, I think. And you're well on your way. For the excellent students, your understanding is sound. See, my problem is that a lot of calculus is taught in steps. Step 1, step 2, step 3. So if you're looking for the gradient, step 1 differentiate, step 2 substitute x in. I don't like that, right? Because if the examiner moves a little away from what the book is teaching you, you're lost. But if you know how to use a toolkit, then whatever the examiner throws your way, you're ready for it. You know what's up. You know how to. You're agile. And you know what you're doing. Really, you know why you're doing what you're doing, which is amazing. It's a great feeling when I do that. That's why I love maths. Right? So common uses. Okay, so sorry. Let's see a question from an example. Okay? Well, it's not from an example. It's exactly like what you will get from it. So the point 0.04 lies on the function blah blah blah. What is the gradient of the tangent at that point? Now, firstly, little tip: when they say gradient of the tangent, that's the same as gradient. So you don't need to worry about that part because the gradient at the point is equal to the gradient of the tangent at that point. It's just kind of tricky. So it's a little bit of jargon you need to know, right? So you're really looking for the gradient at this point over here. Now, first thing I advise, first thing in a calculus question, write down what you know and what you're looking for. Because if you realize what you know, then you can go to your toolkit and use it appropriately based on what you have. So looking at this, I can see that I've got this point. I'm going to write x equals 0 and y equals 4. I also have this function, f of x equals 4x squared plus 2x minus 4. That's everything I have. The next thing I'm going to write down is what am I looking for? I'm looking for the tangent. Sorry, the gradient of the tangent, which is basically the gradient. I want to know the gradient. And I go back to my toolkit and I look at the gradient and I ask myself, okay, I need the gradient. You can find, no, that's not the gradient. You can find, no, that's not the gradient. You can find, ooh, that's the gradient. Okay, so it's very clear what I have to do. I have to have x. I have to have a gradient function. And I have to put x into the gradient function to spit out the gradient. Let's do that. So let's make a gradient function. Natural. It's a what's it called? Let's say. Oh, that's not the gradient function. Okay. Hopefully I've got it right now. Okay, so hopefully I've got it right now. It's really hard to do algebra typed. It's much easier with writing. The first thing is I get the gradient function, so I appreciate that. And then what did I say? I need x. And do I have x? Yes, I do. I put it in there, and it gives me a gradient of 2, which is actually really cool. That is that what I was looking for? Yep, that's the answer. Just beware, like some people might be suspicious. They gave me y equals 4 and I didn't need it. That's very common in this exam, right? They give you some superfluous information you don't need, right? So don't worry about that. You've got your answer, and the gradient at 0, 4, the gradient will be 2, which was quite good. Okay, that's a very simple question. Let's look at a more challenging one. What is the gradient of f of that function when the function is at 1? I'm sorry, that's just not very good. I was just in a hurry. I don't know how to word this well. But basically saying when the function is at 1 on in the y-axis direction, when considering the y-axis, what is the gradient? Okay. So firstly, when I say the first thing you do, write down what you know. So you know that y equals 1, and you know this is your function. Then write down what you're looking for. It says what is the gradient. So we're looking for the gradient, right? Now we're looking for the gradient. Now let me show you my processes, okay? Where is it? There we go. So this is how I would think about it, okay? It would be like, I need the gradient. So I need this, right? In order to find the gradient, it says I need to substitute x into the gradient function. Okay, I don't have x, and I don't have the gradient function. So now my whole effort should be, is there any way I can find x, and is there any way I can find the gradient function? You can do it in any order you want, but I think the gradient function is the easiest, because obviously you just need. So I'm going to find that first, right? So I'm going to go to my function, I'm going to differentiate. So I'm going to take 3 over here, so it's negative 12x squared plus 2x minus 7. So I found my gradient function. So half of the problem is over. I found the gradient function. Now what else did it say over there? Okay, so now I can put a tick over here. I did my efforts and I found the gradient. I don't have x. And I'm looking at the question and I can't find x. God, I wish there was a way you could find x. Is that x? No. Is that x? Yes. This will find you x. Is that x? No. Also this will find you x. So if I know the gradient, like as a number, I can find the x for which that is true. Or if I know y, I can find the x for which that is true. Now you have to ask yourself, you go back to what you have. I don't have the gradient as a number. The gradient is what I'm looking for. So I can't use that. But I do have y. Sorry, ran out of battery. So what I was saying is that I need to find x, and although there were two ways of doing that, the only one that I will be effective in is this one, because I do have y, and that is the great advantage. That is the great advantage of writing down what you have at the beginning. The fact that you have y tells you it's very easy to find x. Just put it into the function. Now be very careful here. Don't substitute y equals 1 in here. This is the gradient function. Okay? Put it in here. Y equals 1. Okay? Again, we ask, so we make it equal to 1. We ask ourselves, is that calculator work or is that an equation? Okay, it's an equation. Okay, is it a linear equation? No, it's x cubed and x squared and all that. So that means is we're going to have to get it equal to 0. So put the 1 on the other side. Just be careful. You're minusing 1 from like terms. None of these are like terms. You just put it on the end. And then now it's just calculator work. Put it in your calculator. You get x equals negative 0.9. But again, that was not what the question asked of us. It asked us what is the gradient. So we look back at our toolkit and we say, okay, now that I've done this, I have a gradient function, I have an x value, and I'm looking for the gradient. Now I have everything I need. I simply put my x into the gradient function, and it will spit out the gradient. Let's do that. This is where we were. We have everything we need. We're going to substitute x into the gradient function. So here's the gradient function. Make every single x. This is a really tricky one for some people. You have to make every single x, not just the first x, into 0.1. I've done that over here. Now you ask yourself, is that algebra or is that calculator work? It's calculator work. Okay, put it in your calculator, you'll get and what that essentially means is that when the function is going through y equals 1, the gradient is negative 7.5. In fact, when it's going through y equals 1, it's also going through x equals negative 0.139, and the gradient is negative 7.